Perspective Class 11 Video 1. In this video we're going to continue talking about central projection. In particular we're going to talk about something called vanishing points. Now vanishing points are a phenomenon which occurs in central projection when you centrally project lines. Okay, so whenever you centrally project a line there's a chance that you'll create a vanishing point. To keep things simple in this particular video we're only going to consider centrally projecting lines which are parallel to the x-axis. In future videos we'll deal with more general lines. So let's look at a geometric picture of what's going on. So here's 3D space. It doesn't look like 3D space, but it is 3D space. The y-axis goes straight into the page. Okay, so you can't see the y-axis because I'm looking perfectly side on. There's a viewing plane, x equals d. It looks like a line, but it's not, it's a plane. And there's actually a line, this pink line here. And I'm going to centrally project this line onto the red viewing plane. So the way I do that is I draw a line of sight, and then I mark wherever it crosses the red viewing plane. So I draw a line of sight, and I mark. Draw a line of sight, mark. Draw a line of sight, mark, and so on and so on. Okay, and you notice that the further I go away from the eye along the line, the closer these points get to one another. Like these two, and then these two are closer, these two are closer, these two are closer, and if I do another one, it will be super close. Okay. And the idea is they get so close that eventually they sort of they stop getting any distance apart at all. They sort of converge to a point, and that point to which they converge is called the vanishing point. Okay, this is like the geometric intuition for what's going on. Let's do an explicit example. So let's look at this line right here, 266 plus t times 100. Because the direction vector is 100, this means that this line is parallel to the x-axis, right? Because the direction vector points in the same direction as the x-axis. And I want to centrally project this line onto the plane x equals 1. So how do I do this? Well, one thing you could do is you could test a bunch of points. Okay, so for example, if I plug in t equals 0, I get 266 plus 0 times 100, which is simply 266. And if I centrally project this onto the plane x equals 1, I get 1 times 1, 6 over 2, 6 over 2, which is the same as 133. Okay, well, let's do a different one. Let's try t equals 1. This time I get 266 plus 1 times 100, which is 366, which gets mapped to 1 times 1, 6 over 3, 6 over 3, which is 122. Okay, how about if I do t equals 2? Actually, 2 is too small a number. Let's do 10. Right, let's see what happens when I do t equals 10. So that's 266 plus 1 times 100. I'm sorry, plus 10 times 100. So I'll erase this. Plus 10 times 100. So that's 1266. And this gets mapped to 1, 6 over 12, 6 over 12, which is just 1, a half. Okay, let's do even bigger. Let's do t equals 100. So this is 266 plus 100 times 100. So what is this nowadays? That's like 102, 6, 6. which gets mapped to 1 times 1, 6 divided by 102, 6 divided by 102. Which, if you work this out, I think this is 1/17th, 1/17th. Okay? So the idea is I'm taking t bigger and bigger and bigger, and I'm looking for a pattern in the image. Okay? And it seems reasonable to guess that as t goes towards infinity, the image point goes to 1, 0, 0. Like, these numbers here are just getting smaller and smaller and smaller every time I make t bigger. They go from 3, 3, and then to 2, and then a half, and then a 17th. And as I make t bigger, these numbers are just going to get smaller and smaller and smaller. I mean, the 17th is already pretty small. But as t goes like to infinity, so if t is like a million or a billion or something, they're probably going to be super small. So it looks like as t gets bigger, the image point goes to 1, 0, 0. Well, we can show this more formally using a bit of algebra. Okay, so we want to show this statement here. Right now, I just have like evidence to suggest that this is true, but I want to sort of prove that this is true. So how can I do that? Well, what I can do is I can consider a general point. Consider a general point on the line. Okay, so what is a general point? That's 2, 6, 6 plus t times 1, 0, 0, which I can rewrite as 2 plus t, 6, 6. I just combined these vectors, right? We spent a long time doing vector arithmetic, so this should be not too hard. And then I can centrally project this point right here. So centrally projecting this point right here is going to give me 1, 1, 6 divided by 2 plus t, comma, 6 divided by 2 plus t, which is just equal to 1, 6 divided by 2 plus t, 6 divided by 2 plus t. And now the question is, well, what happens to this as t goes to infinity? So as t gets really, really big, that's what this notation means. As t goes towards infinity, as t gets really big, what happens to this thing right here? Well, let's think about this. As t gets really, really big, the first coordinate's not going to change at all because there's no t in this coordinate. Okay, so as t gets really, really big, the 1 is going to stay the 1. But this coordinate and this coordinate, what do? Well, the numerators stay the same. The numerators are 6 in either case. But the denominator is 2 plus t. And as t gets big, this is going to get really, really big. So that means this fraction is going to be like a fixed number divided by something which gets really big, which means the whole fraction is going to get really small. So as t goes towards infinity, what happens is this thing goes towards 1, 0, 0. Okay? As t goes towards infinity, this vector right here tends towards 1, 0, 0. And we say that 1, 0, 0 is the vanishing point. Of the line. Okay, so if we were to try and plot this line, what would it look like? If we were to try and plot the image of this line after we centrally project it, what would that look like? Well, I'll draw a coordinate axis. I'll label it, this is the x equals 1 plane, which means that this is y, this is z, 1, 2, 3, 1, 2, 3. And we know that the vanishing point is 1, 0, 0. We know that that's the vanishing point, okay? Well, I'm already on the x equals 1 plane, so ignore the 1. It means I just plot this point here. This point here is the vanishing point. But what does the rest of the line look like? Well, we can work that out by taking one of our test points. So for example, we know that when t is equal to 0, then the point gets mapped to 1, 3, 3. So that means I can go down here, go to 3, 3. Okay, this point here corresponds to t equals 0. When t is equal to 1, I know it goes to 1, 2, 2. So this point here corresponds to t equals 1. When t is equal to 10, it goes to 1, 1/2, 1/2. So that's this point here. This corresponds to t equals 10. When t is equal to 100, it goes to a 17th, a 17th, which I can't draw accurately, but this is good enough. That corresponds to t equals 100. And as t gets bigger and bigger and bigger, it's going to tend towards the origin, the vanishing point. Okay, so the line in general is going to look like this. To get these points, you need to plug in negative t, but that's okay, that's acceptable. Okay, but there's no way that you'll get these points down here. It never goes past the vanishing point. Okay, it never goes past the vanishing point. So this is what the line would look like if you were observing it from the origin and the viewing plane was x equals 1. So we can see some examples of this happening in real life. Because central projection is the type of projection which most closely replicates what we see with our eyes and what a camera does when it takes a picture, like this phenomenon is readily seen in the real world. So for example, here's a picture of some train tracks, okay? And there's a bunch of lines going directly away from you, okay? Like imagine the x-axis goes straight in front of you. And all of these lines, they seem to converge to this point on the horizon, which is the vanishing point. Okay? They all seem to meet at the vanishing point. Another example is this picture right here. So there's like parallel lines here and here, and they're going directly away from you. But notice how they tend to converge at the vanishing point in the distance. Okay? And this is exactly what happened in the algebraic example we just did. Okay? This picture here is a real life example of exactly what happened in that example with algebra. That's the end of this video.